I first encountered the substation on East 16th Street in Brooklyn, officially recorded as completed in 1892, during what I assumed would be routine research into early electric streetcar infrastructure. City records described it plainly, a late 19th century traction power building constructed to support Brooklyn's expanding trolley network. Nothing unusual. Brick, steel, municipal. An 1894 construction photograph from the Brooklyn Rapid Transit Archives showed the building nearly complete. I almost closed the folder until I noticed the lower facade. The stone courses beneath street level were not brick at all, but precision-cut granite, fitted so tightly that no mortar line was visible even in high-resolution scans. The symmetry was exact. The curvature beneath the windows suggested a sealed sublevel rather than a foundation. This should not exist in a hastily built streetcar substation. In the margins of the photograph, an engineer had penciled a note that read, "Existing chamber retained." Retained from what? Some researchers would later classify this kind of buried, overbuilt infrastructure as Tartarian, inherited, rather than constructed. At the time, I only felt the discomfort of realizing I was no longer looking at an ordinary 19th century building. The historical narrative is tidy. Brooklyn's electric streetcars expanded rapidly after 1889, driven by new overhead power systems and municipal investment. The East 16th Street substation was attributed to William J. Wilgus, an engineer associated with early traction electrification projects. Official documents describe brick masonry, steel trusses, and rotating converters. Nothing exotic. Yet the Sanborn Fire Insurance Map from 1891 already depicts the substation footprint before the documented construction date. The outline matches the current building precisely, including a subterranean annex marked only as vault. That vault is never explained. Brick streetcar substations were meant to be cheap, fast, and utilitarian. The Brooklyn Rapid Transit Company built dozens of them across the borough between 1889 and 1895, standardized structures designed for rapid deployment. But standing inside the building today, the interior geometry contradicts that purpose. The arches are oversized, rising nearly 5 meters where 3 would suffice. The wall thickness exceeds structural necessity by a factor of 2. The foundation descends at least 4 meters below grade, far deeper than required for stability in Brooklyn's sandy soil. This was not designed around machines, it was designed around pressure and load. The official plans, preserved in the municipal archives, show electrical equipment layouts but provide no foundation details. Where Victorian engineers would typically include cross-sections showing bedrock engagement, soil composition, and load-bearing calculations, these plans simply note existing substructure with no further elaboration. Some researchers note that Tartarian infrastructure often appears as repurposed shells beneath later industrial systems. At this stage, I dismissed that idea. The term itself felt too exotic, too convenient. Still, the map remained open on my desk longer than expected, the vault outline traced in faded blue ink. If the vault predated the building, what exactly was being electrified or reused? Examining the 1893 renovation ledger, I noticed repeated references to facing brick applied over existing masonry. The phrasing is careful, not foundation, not support. Close inspection photographs from a 2012 structural survey reveal that the lower 3 meters of the structure are not brick at all. They are stone blocks weighing an estimated 3 to 5 tons each, based on volume calculations and material density typical of Connecticut granite. The blocks measure roughly 1.2 meters in length, 0.6 meters in height, and 0.8 meters in depth. No crane capable of setting these stones existed on Brooklyn streets in the early 1890s. The first steam-powered construction cranes with sufficient capacity did not arrive in New York until approximately 1897, according to engineering journals from the period. Manual block and tackle systems could theoretically move such weights, but the precision of placement would have been impossible. Symmetry is exact to within millimeters. Modern laser scanning conducted during a 2015 utilities upgrade measured the alignment of the granite courses at a tolerance of less than 2 millimeters across a 12-meter span. Even modern CNC stone cutting struggles to maintain this tolerance at scale without computer guidance. This precision appears repeatedly in what Tartarian researchers identify as architectural signatures, especially in buried or partially buried infrastructure, later reclassified as industrial. The thick walls, the oversized arches, the precision stonework beneath brick facades, these features appear in structures across Europe and Asia in regions once labeled Tartaria on 18th century maps. The official explanation, offered in a 1923 city engineering report, suggests reuse of old retaining walls from previous riverbank construction. But the East 16th Street site is nowhere near the original Brooklyn waterfront. Retaining walls do not require perfect curvature, nor do they align with internal conduit systems visible in the photographs. I remember writing in my notes, "This is not accidental reuse, this is intentional inheritance." During a site visit in 2018, I photographed a sealed archway beneath what is now a utility corridor. The arch is constructed from the same granite as the lower facade, not brick. Its keystone bears no date, no maker's mark, unusual for Victorian infrastructure, which typically included cornerstone inscriptions or foundry stamps. The arch spans approximately 2.4 meters and stands 3.2 meters high. The voussoirs, the wedge-shaped stones forming the arch, are cut with such precision that the joints remain nearly invisible, even where the mortar has deteriorated. This level of stone dressing was rare in American construction of the 1890s and was typically reserved for monumental civic buildings, not industrial substations. A 1907 maintenance log from the Brooklyn Rapid Transit Company mentions that lower access was sealed following decommission of hydraulic apparatus. Hydraulic apparatus? Streetcars of the 1890s were electric, not hydraulic. The overhead wire system, introduced by Frank Sprague in Richmond, Virginia in 1888, had become the standard by the time Brooklyn's network expanded. No public record explains what hydraulic system existed beneath the substation or why it was removed. I searched through Water Authority archives, expecting perhaps a confusion with hydraulic elevators or water pumps. Nothing matched. The hydraulic systems documented in Brooklyn during that period were associated with industrial presses, dock machinery, and a few experimental elevator installations in downtown buildings. None were located near East 16th Street. Tartaria researchers often point to buried hydraulic networks as remnants of a pre-industrial power distribution system later misunderstood or dismantled. The theory suggests that regions marked as Tartaria on older maps possessed sophisticated infrastructure for distributing mechanical energy through pressurized water systems. I did not accept that conclusion, but the absence of explanation was itself a fact. Why seal a doorway instead of documenting what lay beyond? Why describe equipment as decommissioned when no record exists of its commission? The official story had already begun to thin. Before moving deeper, I paused to contextualize the Tartaria claim itself. Guillaume Delisle's 1706 map, Carte de Tartarie, labels vast regions of Eurasia, from the Caspian Sea to the Pacific, as Tartaria or its subdivisions, Tartarie Chinoise, Tartaria Independente, Tartaria Muscovite. By the mid-1800s, the term disappears from cartography, replaced by nation-states and colonial borders, the Russian Empire, China, Mongolia, Turkestan. Mainstream historians treat Tartaria as a vague geographic label applied by European mapmakers to poorly understood territories. The term derives from Tatar, the name given to various Turkic and Mongolic peoples. It was never, in academic consensus, a unified civilization or empire. Alternative researchers argue otherwise. They point to the sudden cartographic erasure, the architectural consistency across former Tartarian regions, and the lack of construction documentation for many 19th century buildings. In this view, Tartaria represents a forgotten infrastructure-based empire deliberately obscured through historical revision. Standing in Brooklyn, that debate felt abstract until I realized the architectural traits identified as Tartarian appeared here: buried systems, oversized masonry, precision beyond documented technological capacity, hydraulic infrastructure in electric age buildings. Photographs from the 1890s show nearly identical substation designs in cities thousands of miles apart: St. Petersburg, Melbourne, Berlin. The same proportions, the same stone beneath brick construction, the same unexplained vaults. The map was not evidence, but the pattern was beginning to form, and patterns are where architecture stops being neutral. I returned to the photograph of the sealed archway, the granite keystone precisely cut, bearing no mark. In the lower right corner of the image, barely visible, was a notation in faded pencil that read, "Pre-existing structure incorporated 1892. Pre-existing. If the granite chambers predated the electrical system, what had they been built to contain? The 1892 electrical plans held in the New York Public Library's Irma and Paul Milstein Division of United States History show generators and converters occupying the main hall. These machines, manufactured by General Electric and the Thomson-Houston Company, are documented in procurement records and installation photographs, but the plans show no foundation details beneath the machines, only a blank space labeled "Existing Substructure." This omission is striking. Victorian engineers documented foundations meticulously, particularly for heavy rotating machinery that generated vibration and required precise leveling. Standard practice included detailed drawings showing foundation depth, composition, anchor, bolt placement, and bedrock engagement. The Thomson-Houston rotary converters installed in 1892 weighed approximately 12 tons each. Supporting such equipment required engineered foundations calculated to prevent settlement and vibration damage. Yet the plans provide no such calculations. Photographs taken during a 1911 equipment upgrade reveal conduits descending far below the machine floor. The conduits are iron pipes, 30 centimeters in diameter, with flange joints, inconsistent with electrical wiring of the period. They descend at least 6 meters below grade, far deeper than electrical grounding requires, which typically extends no more than 2 meters. These conduits align with sealed channels visible in ground-penetrating radar scans conducted during the 2015 utilities upgrade. The scans show a network of horizontal passages radiating from beneath the substation, extending at least 40 meters in multiple directions before the signal becomes unclear. The geometry mirrors that seen in old European tram depots, particularly in cities once bordering regions labeled Tartaria on historical maps. The Vasilievsky Island station in St. Petersburg shows identical features: buried conduits, sealed granite chambers, vertical shafts descending far below operational necessity. Coincidence is possible when examining a single structure. Repetition across continents, in an era before international engineering standardization, is harder to dismiss. The electrical systems were clearly added, but to what? I expanded the search. In St. Petersburg, the Vasilievsky Island tram power station, officially completed in 1902, displays the same features: buried stone chambers beneath brick facades, sealed arches, and walls far thicker than structural analysis would require. Russian archives include a photograph from May 1901 preserved in the Russian State Historical Archive, showing workers installing electrical equipment inside an already standing stone shell. The interior is clearly ancient, with deteriorated plaster, water staining, and iron fixtures corroded beyond recognition. The workers are positioning new machinery among the ruins of something older. The caption reads, "Adaptation of existing structure for electrical service." The photograph is dated May 1901. The official construction records for the Vasilievsky station claim groundbreaking occurred in January 1901 and completion in December 1902. Yet the photograph shows a structure that appears to have stood for decades, if not longer. Similar documentation exists for the Spencer Street powerhouse in Melbourne, completed in 1890. Construction photographs show workers excavating around pre-existing granite foundations. A notation in the project engineer's diary, held by the State Library of Victoria, remarks that foundation work was simplified by the presence of prior stonework of unknown origin, and that excavation costs were considerably lower. Tartarian researchers frequently cite Russian infrastructure as inheriting Tartarian systems, particularly in cities like St. Petersburg that lie in territories marked as Tartary Muscovite on 18th century maps. I remained cautious. Inheritance does not prove design origin. But the architectural DNA was unmistakable. Brick over stone. Machines inserted into something older. Electrical systems layered onto hydraulic infrastructure. The same streetcar story, repeating across continents, in cities separated by oceans and language barriers, built by different companies during the same narrow window of the 1890s. Either a remarkable engineering coincidence or a systematic adaptation of pre-existing structures. Returning to Brooklyn, I reviewed Water Authority diagrams from 1888, predating the substation by 4 years. These diagrams, stored in the Brooklyn Historical Society archives, show the city's water and sewer infrastructure in precise detail. Beneath East 16th Street, the diagrams show pressurized channels unrelated to sewage or potable water supply. They are marked in red ink, the notation used for non-municipal infrastructure. A marginal note, written in a different hand, reads, "Legacy conduits, do not disturb." Legacy conduits. From what legacy? Hydraulic pressure systems were rare, expensive, and unnecessary for streetcar operations. The few hydraulic power networks that existed in American cities were used primarily for operating elevators, dock cranes, and industrial presses. London had a more extensive system. New York's Manhattan system, established in 1894, served a limited district and was considered economically marginal. Yet the conduits beneath East 16th Street align perfectly with the sealed granite chambers. Ground-penetrating radar data shows the channels connecting to the buried arches, forming a network that extends beneath multiple city blocks. The channels are lined with what appears to be glazed ceramic or possibly vitrified clay, materials used in pressurized hydraulic systems to prevent leakage and corrosion. The diameter and construction technique match hydraulic mains documented in European cities during the mid-19th century. Tartarian theorists argue that such systems once distributed energy via pressure and flow, part of a sophisticated infrastructure later stripped out as obsolete when electrical systems became dominant. The theory suggests that Tartarian civilization possessed advanced hydraulic engineering, using water pressure to transmit mechanical power across cities. I do not assert this. But the physical alignment is real. The conduits exist, the chambers exist, the sealed arches exist. Electric streetcars appear to have been layered on top of something else. Something already there, already functional, already sealed by the time the electrical equipment arrived. One detail refused to leave my mind: a shallow dome integrated into the substation roofline, officially described in the 1892 specifications as a ventilation dome for heat dissipation. The dome measures 4.8 meters in diameter and rises 1.2 meters above the main roofline. It is constructed of brick with an interior iron framework, typical of industrial architecture from the period. But the proportions are mathematically precise, a perfect hemisphere with a radius matching exactly 1/4 of the building's width. The same dome appears in Melbourne's Spencer Street powerhouse, completed in 1890, identical radius, identical proportions, the same hemispherical geometry. It appears again in Berlin's Moabit tram depot, completed in 1895. Construction photographs from the Landesarchiv Berlin show the dome being integrated into an older building shell, not constructed from the ground up. Ventilation domes do not require perfect hemispherical symmetry. Functional ventilation can be achieved with simple gabled openings or basic cupolas. The mathematical precision serves no ventilational purpose. In architectural catalogues compiled by Tartarian researchers, domes of this specific proportion are cited as pressure-regulating elements rather than decorative features. The theory suggests they functioned as expansion chambers in hydraulic systems, allowing pressure fluctuations to be absorbed without damaging underground conduits. I could not prove that function. The internal structure of the Brooklyn Dome is inaccessible without destructive investigation, and no original engineering drawings explain its internal mechanism. But I could prove repetition. 3 cities, 3 continents, 3 identical domes, built within a 5-year span, incorporated into structures officially described as newly constructed but containing granite foundations that suggest otherwise. Repetition implies design. Identical proportions imply standardization. Standardization across continents in an era before international engineering communication implies either extraordinary coincidence or shared inheritance. The domes were not ornamental, they were too precise, too consistent, too mathematically deliberate. They were signatures. Renovation records from 1923, preserved in the New York City Municipal Archives, describe the removal of obsolete subfloor systems during a modernization project funded by the Brooklyn-Manhattan Transit Corporation. The work orders specify concrete filling of lower chambers and associated machinery housings. They list materials: 340 cubic yards of concrete, 12 tons of demolition rubble, and labor costs for cutting and removal of iron fittings. No diagrams survive showing what was removed. Photographs taken before renovation, found in the BMT Corporate Archives collection, show the subfloor during preparatory demolition. The images reveal valves, iron housings with circular flanges and jointed piping inconsistent with electrical equipment. The fittings are massive, some appear to be 50 centimeters in diameter or larger, and they show design characteristics of hydraulic pressure systems, including heavy wall thickness, flanged connections, and gate valves. After renovation, the floor is smooth concrete. Site photographs from 1924 show a clean, modernized interior with no trace of the previous sub-level complexity. The act of modernization appears to erase complexity rather than explain it. The renovation report describes the removed systems as outdated infrastructure of no historical significance. Yet nothing in the report identifies what the infrastructure was, who built it, or when it was installed. Tartarian researchers argue that this phase, the 1920s wave of urban modernization, represents deliberate simplification, removing systems no longer understood or maintainable. The theory suggests that complex hydraulic networks inherited from Tartarian infrastructure were dismantled during the transition to fully electrified cities. I cannot verify intent, only outcome. What was once there, documented in photographs, described in work orders, and substantial enough to require hundreds of cubic yards of concrete to fill, is gone. Not preserved, not studied, not archived. simply removed and sealed. The renovation was efficient, professional, thorough, and irreversible. Streetcar components from the era, axles, couplings, bearing assemblies, electrical contactors, display machining tolerances difficult to achieve in 19th century workshops, a level of precision that stands out. I examined tram wheel assemblies from the 1890s, preserved in the New York Transit Museum collection. The axles show lathe work with surface finish quality and dimensional precision characteristic of industrial production, not hand tooling. The bearing journals are machined to tolerances of approximately 0.05 millimeters, achievable with period equipment, but requiring skill and time that should be reflected in production costs and manufacturing documentation. Yet engineering journals from the 1890s, particularly the Street Railway Journal and Electrical World, express repeated frustration at unknown suppliers delivering precision components with minimal documentation. An 1892 article notes, certain mechanical elements arrive finished to specification with no indication of manufacturing origin or method. Procurement offices report difficulty obtaining duplicates as original sources cannot be reliably identified. Already finished, already machined to precision, already available as if manufactured by processes or facilities that left no documentary trace. Some researchers speculate inherited manufacturing capacity, workshops, or foundries whose original purpose was lost but whose equipment remained functional. Others suggest undocumented industrial hubs, perhaps operating outside conventional economic records. But when combined with inherited infrastructure, granite chambers predating official construction, hydraulic systems sealed beneath electric substations, identical architectural signatures across continents, the possibility shifts. What if the workshops did not exist because the systems predated the industry? What if the precision components, like the buildings themselves, were adapted rather than created? The streetcar era coincides suspiciously with infrastructure discovery, the sudden availability of precision stonework, machined fittings, buried conduit networks that required only integration with new electrical systems, not construction, adaptation. The machines were new, the structures beneath them were not. Mapping the streetcar substation studied Brooklyn East 16th Street, St. Petersburg, Vasilievsky Island, Melbourne Spencer Street, and Berlin Moabit reveals something I had not initially considered: geometric alignment. Using historical maps and modern global positioning system coordinates, I plotted the locations relative to other 19th century infrastructure in each city. The substations align with star fort geometry, a feature repeatedly associated with Tartarian maps and urban planning. In Brooklyn, the substation sits at a vertex, connecting two former fort positions, Fort Hamilton and the Revolutionary War-era fortifications near Gowanus. The angle is precise, 60 degrees, the characteristic angle of star fort bastions. In St. Petersburg, the Vasilievsky station aligns with the Peter and Paul fortress and the Alexander Nevsky monastery, both structures predating the city's official founding in 1703, and both incorporating geometry inconsistent with Russian Orthodox or Petrine architectural traditions. The substations sit on geometric nodes, not random parcels selected for real estate convenience. Urban planners in the 1890s did not design cities this way. Site selection for industrial infrastructure followed practical criteria: proximity to rail lines, access to water for cooling, availability of cheap land, and distance from residential areas to minimize noise complaints. But someone may have earlier. If the buried infrastructure predated the streetcar systems, if the granite chambers and hydraulic networks were inherited rather than constructed, then the geometric pattern might reflect an older urban design principle. Tartarian researchers argue that cities across Eurasia show evidence of geometric planning inconsistent with documented historical development. suggesting an earlier civilization that designed settlements around mathematical principles later obscured by conventional construction. The alignment is not proof, it is pattern. But pattern repeated across continents, connecting structures built by different companies in different decades, suggests either intentional coordination or shared inheritance from a pre-existing template. The geometry remembers what the documents do not. Chapter 11. By this stage, my assumption had quietly inverted. I had begun investigating these substations as Victorian achievements with curious anomalies, odd foundations, oversized chambers, unexplained hydraulic traces. Now I could no longer sustain that framework. These were not Victorian achievements, they were Victorian adaptations. The precision stonework predated the brick facades. The hydraulic systems predated the electrical equipment. The geometric alignments predated the streetcar networks. The 1890s did not create this infrastructure, the 1890s occupied it. The official narrative, rapid urban industrialization, technological triumph, the birth of modern transit, remains factually accurate in its surface details. Electric streetcars did revolutionize urban transportation. Engineers like Sprague and Wilgus did pioneer new systems. Brooklyn's network did expand dramatically between 1889 and 1900. But beneath that narrative lies physical evidence that cannot be explained by it. Granite blocks too heavy for period equipment, machining tolerances beyond documented capability, hydraulic networks serving no electrical purpose, identical architectural signatures separated by oceans. Tartaria, in this framing, is not a lost fantasy civilization. It is a name, imperfect, contested, perhaps inadequate, given to an unresolved inheritance. The structures themselves do not care what we call them. The granite remains precisely cut, the chambers remain sealed, the geometric alignments remain measurable. We adapted what we found, we integrated it into our systems, we built upon it, covered it, modernized it, and then we forgot it had been there first. The investigation did not reveal certainty, it revealed the absence of certainty in the official record and the presence of physical complexity that record cannot account for. What came before the streetcars? Who cut the granite? Why were the chambers sealed? I do not know, but I know the questions are real. Chapter 12. I returned to the sealed archway beneath East 16th Street one final time, this time with better lighting and measurement tools. The granite keystone, examined closely, shows no tool marks consistent with 19th century stone dressing. The surface is too smooth, the edges too crisp. Modern diamond tooling produces this finish. So does ancient bronze tooling given sufficient time and skill. But neither should exist in Brooklyn in the 1890s. The arch remains sealed. The 1907 maintenance order specified concrete fill, permanent closure. Ground-penetrating radar confirmed solid mass behind the stonework. The chamber beyond was filled, not merely blocked. What was removed before the sealing? The maintenance log mentions hydraulic apparatus, but provides no inventory, no description, no disposition record. The equipment simply disappears from documentation between the mention of decommissioning and the order to seal. Once I saw this archway as a curiosity, an odd detail in an otherwise straightforward building history. Now it appears as a deliberate boundary between eras, a threshold we crossed without documentation, sealing behind us what we did not understand or could not maintain. The stone remains, the precision remains, the alignment with distant structures remains. We did not build this, we adapted it, we layered our systems onto something older, then covered the junction points with brick and concrete until the original structure became invisible beneath the renovations. The official history is not false, it is incomplete, and the gap between what is documented and what physically exists is where Tartaria resides, not as proven fact, but as persistent question. The archway will remain sealed. The chambers will remain filled. The questions will remain unanswered. But the granite does not require our answers. It was here before us. It will outlast our explanations. Chapter 13. Final Echo. The last image I studied was not dramatic. An 1894 photograph, corner torn, shows a worker leaning against the granite wall, small beside it. He wears work clothes typical of the period, heavy canvas trousers, a vest, a cloth cap. His hand rests on the stone, casual, unaware that the block beneath his palm weighs several tons and was set with precision his era's equipment could not achieve. The caption, written in faded brown ink, reads simply, "Powerhouse Interior." No mention of what came before, no acknowledgement of inheritance, no explanation of the granite beneath the brick, the hydraulic conduits beneath the electrical systems, the sealed chambers beneath later renovations. The worker is long dead. The electrical systems he installed were replaced decades ago. The streetcars stopped running in 1956, but the wall remains, precise, aligned, silent. It does not care what we call it, Tartarian, Victorian, industrial, mysterious, it simply is. And across the world, in St. Petersburg, Melbourne and Berlin, identical walls stand in identical substations built in the same narrow window of years, on the same geometric nodes, above the same sealed chambers. The pattern persists, the questions persist. The granite remembers what we have forgotten.